Inside a quantum computer, what's actually happening?
Right now, somewhere in the world, there are machines that don't behave like anything you've ever used before. They don't follow normal logic. They don't process information step by step. And they don't think the way your phone or laptop does. Instead, they operate in a strange world where things can exist in multiple states at once, where particles can influence each other instantly, and where the answer to a problem is not calculated directly, but emerges from probability itself. These machines are called quantum computers. And today, we are not just talking about them, we are going inside. We will open the machine, strip away the confusion, and walk through, step by step, what actually happens inside a quantum computer while it works. No hype. No shortcuts. No unnecessary complexity. Just a clear, visual understanding of one of the most powerful technologies humanity has ever created.
What you expect versus reality.
When most people hear the word computer, they imagine something familiar. A laptop. A phone. A server. Something with a screen, a keyboard, apps, and files, but when you see a quantum computer for the first time, you realize immediately. This is not the same category of machine. It doesn't look digital. It doesn't look interactive. It looks experimental. A typical quantum computer looks like a tall metal structure, covered in wires and tubes, suspended in layers often inside a sealed chamber. Some people say it looks like a golden chandelier. Others say it looks like scientific art. But here's the truth. What you're seeing is not the computer itself, it's the life support system. Because the real computation happens at a level so fragile, that it cannot survive normal conditions.
Why quantum computers need extreme conditions?
To understand this, imagine trying to balance a pencil on its tip. Now imagine doing that, in a moving car, during a storm, while someone is shaking the table. Impossible, right? That's what it's like trying to maintain a qubit in a normal environment. Qubits are extremely sensitive. They are affected by heat, vibration, light, radiation, even tiny electromagnetic noise, so scientists had to create a solution. They removed almost all external interference. This is why quantum computers operate at temperatures close to -273 degrees Celsius, which is colder than outer space. At this temperature, atomic motion slows down, noise is minimized and quantum states can survive longer. But even then, they only last for a very short time. This fragility is called decoherence, and it is one of the biggest reasons quantum computing is still developing.
Understanding qubits without confusion.
Let's simplify this completely. A classical bit is like a switch, with the bit having 0 as off and 1 as on. A qubit is not a switch. It's more like a spinning object. Imagine a globe with 0 as the North Pole and 1 as the South Pole, but the qubit can exist anywhere on the surface of that globe. Meaning it can be 0, 1, or a combination of both. This is called superposition. But here's the key insight most people miss. It's not just both at once, it's a range of probabilities. A qubit is not choosing between 0 and 1, it is balancing between them. Everything you've ever done on a computer, every message you've sent, every video you've watched, every password you've ever created, relies on a very simple rule. A rule so basic that you probably never even think about it. That rule is this. A computer must choose 0 or 1. Yes or no. True or false. Every single digital system in the world is built on that foundation. But what if that rule was never absolute? What if there was a way, for a machine to not choose? To exist in a space where 0 and 1 happen at the same time? Where answers are not calculated step by step, but emerge from a sea of possibilities. That is the idea behind quantum computing. And once you understand it, you start to realize something deeper. This isn't just a new kind of computer, it's a completely different way of thinking. And by the end of this video, you won't just know what quantum computing is, you'll actually be able to picture it happening.
Why do we even need quantum computing?
Let's ground this in reality. Because without understanding the problem, quantum computing won't feel important.
First is the search problem.
Imagine this. You are given a locked vault. Inside it is something incredibly valuable. But there are 10 million possible keys. A classical computer approaches this logically. It tries key 1, tries key 2, tries key 3, and keeps trying. Even if it can test thousands per second, it still moves step by step. Now scale this problem up. Breaking encryption, simulating molecules, optimizing global systems. These problems become so complex that even the fastest supercomputers struggle.
Second is the real-world limit.
Some problems would take thousands, or even millions of years for classical computers to solve, not because computers are slow, but because the method itself has limits. Now imagine a different approach of not trying one key at a time, but exploring many possibilities simultaneously. Not by speed, but by changing the rules of computation itself. That's the leap quantum computing makes.
Deep clarity of classical computers.
Before we go further, we need to clearly understand the system we're replacing. Every classical computer uses bits. A bit is like a tiny switch with off for 0 and on for 1. That's it. From this simple rule, everything is built. Images, videos, games, artificial intelligence. Even the most advanced AI still operates on billions of tiny yes or no decisions. Think of classical computing like walking through a maze, one path at a time. You can move fast, but you still have to follow the paths. Now we change everything. A qubit is not a switch. It's better imagined as a sphere of possibilities. Top equals 0. Bottom equals 1. Every point in between equals a combination of 0 and 1. Imagine a dimmer switch instead of a light switch. Not just on or OFF, but every possible brightness level in between. Now imagine that in multiple dimensions. That's a qubit. A qubit doesn't decide between 0 and 1, it exists across them.
Superposition.
This is where things get interesting. Superposition is when a system exists in multiple states at once. Imagine listening to music. A single note is simple. But a chord? Multiple notes at once. A qubit is like a chord of possibilities. Think of multiple versions of a reality. In one, the answer is A. In another, the answer is B. In another, the answer is C. Quantum systems explore these possibilities together. This does not mean that the computer magically knows everything. Instead, it represents many possibilities at once and then processes them intelligently.
Entanglement.
Now we reach one of the most powerful ideas. The basic idea is that entanglement links qubits together. The deep analogy. Imagine two dancers. No matter how far apart they are, when one moves, the other moves instantly in sync. This matters as it allows quantum computers to coordinate information across multiple qubits and solve problems as a connected system. Entanglement turns individual qubits into a unified system of intelligence.
Step-by-step computation.
Now let's slow everything down. Step 1. Initialization sets the system, like preparing a chessboard. Step 2. Superposition expand possibilities. Step 3. Entanglement links the system. Step 4. Quantum gates guides the system, not flipping switches but rotating probabilities. Step 5. Measurement collapses into one answer. Quantum computing is not about brute force, it's about precision in probability.
Real-world applications.
Let's connect this to reality. 1. In cybersecurity. It can break encryption. It can create new secure systems. 2. In medicine. It can simulate molecules. It helps in discovering drugs faster. 3. In AI. It helps in improving optimization problems. 4. In finance. It helps in better predictions and modeling. 5. For climate. It helps in simulating complex environmental systems.
The danger side.
Every powerful technology has two sides. The risk. If quantum computers become powerful enough, current encryption could become useless. Realization moment. Everything protected today could become exposed tomorrow.
Why we're not there yet.
The challenges include fragility, errors, scaling, cooling. Each qubit adds complexity. Quantum computing is not just about speed. It's about a new model of reality, a new model of computation. Now you understand quantum computing. But the real question goes: who is winning the quantum race? And what happens when they succeed? Let us go ahead and see how encryption works to see how our data is being secured as of now. That's what we explore next. Please subscribe. Because this is just the beginning. The next episode could save you years of regret.